Hello, everyone. This is Professor Ma, and this is the introductions on the sections on curls and Stoke theorems. Given a 3D vector field, think of flow fields or force field, gravitational force fields in three-dimensional space. We define the following vector fields associated with it to be the determinants of this matrix. Okay, and this is called the curls of F. And in physics, they will show you that this actually have something to do with small motions, rotational motions. So yeah, so I'll leave that up to the physicists to explain to you. But for us, oh, by the way, this is what happens if I do expand the operations. Then basically these parcels you have to take delta uh, part with respect to h, respect to y, subtract the part with respect to g, and then you have to do respect to the z. You have to do this and then the ijk components, and you get these vector fields. Okay, and so here is the calculations, and then we'll get this vector field. For us, the first big thing is association with conservative fields. Okay. Remember what we mean by conservative field? I mean a three-dimensional field is conservative field if there is a function x, y, z where del p is precisely this. In other words, when I take the partial respect to x, I get precisely f. When I take partial respect to y, I get the j component. When I take the partial respect to z, I get a k component, the functions, the partial derivative for the ijk components. Uh, well, then the theorem says a 3D vector field is conservative if and only if the curl is zero. And so we can check easily that this particular vector field is conservative. You just check the derivatives of the subtraction of the difference of the partial derivative in three components ijk, they all come out zero. So 0, 0, 0. So this is conservative. And then if we want to find the potential functions, we'll integrate it backwards. So this is the derivative with respect to the x. So I integrate it with respect to x to recover the p. And if I take the antiderivative with respect to s, I get x squared y plus 3x, plus other things in k and z, okay, which disappear when we take the derivative with respect to dx. And we take these partially reviewed answers, we take the derivative of this now with respect to y to compare it to what it's supposed to be. Oops, the y is that one. So take this partially reviewed formula with respect to y and compare this with the j components. Oh, we see that the k after the partial derivative is a constant minus 4. And now we do integrate this with respect to y, and I get a function plus z, and then etc. etc. And then finally we get down to the piece. Every piece is reviewed. And then this is the potential function up to constant, of course. Okay. So that's the first big things about curves. So theorems. The Stoke theorems is another usage for the curve. The Stoke theorems it's a generalization of the Green's theorem. The Green's theorem says converts that the integral of the works of vector fields. We converted the vector the works integral into a double integral inside. Okay, so it converts from a curve to work around it into a region inside it. Okay, then it gives you, of course, what's the formula you have to use to integrate. Okay, and this is in that flavor, except in this setting, things sit in three-dimensional space. That is, the C, the curve, is a three-dimensional curve in space. So if you like, we'll just think of it as a sphere. Okay. And then, of course, and then you have a surface that with this as the boundary. Oops, I don't want to go up all the way up. Okay, so you have a surface. Think of it maybe as a soap films. Okay, and the C is the curve, and the sigma is the surface. Okay, and it require us to have the C parameterized counterclockwise. And the way I drew it, I didn't do it right. If I go this way, if I go travel this way, yes, that's correct. If I travel this way, the areas on my left hand side, this is the bottom part of the surface. Okay, and then we have a vector field in three space. I'm going to use blue to represent the vector field. Okay, then the vector field, of course, can represent a flow. So I can calculate two things. Then you can also represent force in three space on the boundary curve C. So we're going to calculate two things. First is the work done on the curve. And then Stokes theorem, we can convert that into a double integral. Similar to Green's theorems, converted into dx dy, in the interval inside area in the plane that enclosed. Except this time, it converts into the surface integral of the surface sigma. In particular, if I have the surface integral, it's going to be the surface integral dotted with the normal vector we calculate, unit normal. Okay, this is the unit normal. Okay, integrate over the surface integral. But remember, this part actually can be simplified when we actually calculate. We actually change it into just the partial without being normalized, because the normalized, the length part cancels in ds, in the ds differential. So here is the usual conversion we really want. Okay, but this has a interpretations that actually is the flow across the flux across the surface. Okay, so that's interesting conversions. Okay, conversions into two integral, a non-standard integral, not a dx dy stuff. Okay, and couple of things about the surface. The surface, when we calculate, we have to dot it with the unit normal. But the unit normal, there are two unit normal. If I want to stick toothpicks on this surface with length 1, and all stand up in perpendicular, there are two ways to do it. I can do it, like this outside, or I can stick it inside. Those are unit normals. And there are two different vectors here, okay? And in this case, if the surface is z is equal to f of xy, then this one is the z component is equal to 1, if you like, it's positive, if you like. That unit normal, we call it the upward unit normal because the z component is positive, so it's pointing in the same direction as the positive z-axis, which is up. Another way of saying it. Okay, and so in the actual calculations of these formulas, this side is a line integral, this side is an area integral from the surface converted into area. So then these particular examples says actually to verify this actually turns out the same. Okay. And first, what's the surface? The surface is a ball sitting upside down like that. The sigma is the surface. And what's the boundary? The C. The C is the curve, which should be indicated is this red curve. Okay. And it's going around in, we're looking at this from the bottom, so it's going around counterclockwise. Okay, so yeah, we're looking at this both on the bottom like that. And so do the surface integral first. We'll calculate the curl. The curl come out to be a constant functions, constant vectors. Okay, and a dot with the unit normal with the surface differentials, but that's the same thing as dotting with the partial normal, okay, without not being normalized. Okay, so that's the integral we want to integrate over what? Over dA. Remember, this is a surface integral. We have to convert it into the domain of the surface. The domain of the surface is that R there. That's that circle. Okay. So we convert it into what? Polar coordinates. Okay. That's a circle of radius R or radius 2. That's 0 for z. So you got a circle radius 2. So integrate from 0 to 2, and the dA's are dr d theta. And then convert x into r theta, etc., etc. And then it calculates 12 pi. Here is the line integral calculations. Okay, so we forget about all the surface up there. So now we're just going to look at this circle, okay, going around like that underneath and we have vector fields, whatever the vector field was F up there. So we have to parameterize the circle. Okay, so here's the parameterization in 3D. The z component is 0. Okay, and that's a vector field, and we replace it by the x, y, z in terms of the parameterization key. And we started with derivative, and we integrate the t from 0 to 2 pi for only one circle. Okay. And then it comes like exactly the same as before. So this verifies the Stoke theorem is true, at least for this case. It is true. Okay. And so that's the interesting theory of Stoke theorems. And the final comment, the Stoke theorems, Green theorems, and divergent theorems, they kind of have the same type of flavor. They're all related, and so you can read the textbook to see how they are related, especially in physics. But for us, this is it. This is the end of the course. Bye-bye. See you later.